Hello again. This is Math 2231 coming to you from the College of DuPage, and the title of this lecture is Derivatives of Exponentials and Logarithms. As always, please be an attentive learner while watching this video. By way of introduction, we've talked about polynomial functions. So for example, we talked about a blue function called y equal x squared, and it looked like this. And we could take the derivative of that, and we would use the formula that the derivative of this would be n times x to the n minus 1. Notice that x is in the base and the 2 is an exponent. So there's a variable in the base and the exponent is a constant. And so the derivative of this one was 2x. We could also talk about y equal x to the fourth. Now that is a skinnier function. It's shown in black here. But again, the derivative of that would be, and we have the same thing, the base is a variable, but the exponent is a constant. The derivative of that would be 4x cubed. And we could also talk about y equal x. The derivative would be 1. And we could also talk about y equals y equal x cubed. And the derivative of that would be 3x squared. So in all of these cases, when we're talking about polynomials, the variable is in the base and a constant is in the numerator. But today we're going to be talking about exponential functions, and an exponential function is different. And you can see the graph is, in fact, very different. And so here we have y equals f of x equal 2 to the x. Notice that the constant is in the base and the variable is an exponent. That makes it grow very fast and drop very quickly. And the inverse of the exponential function is called the logarithm function. Again, as you may recall from your pre-calc, it's the reflection of the blue exponential curve about the line y equal x, and the exponential curve does this, but the logarithm curve drops very, very rapidly here, but grows very slowly as it goes along. And so these are what we're going to be talking about fundamentally are the curves over here. And again, it's very different than the curves over here. And we're also going to be talking about the number e, which is also known as Euler's number. And this is a mathematical constant like pi. And like pi, it never terminates and never repeats, but it's approximately equal to 2.71828. And there is a button on your calculator that has this. And this can be characterized in many ways. It's a very important number. In fact, some people say it's the most important number, and I can't take issue with that. Now, we will review exponentials and logarithms somewhat in the context of our calculus problems, but more extensive reviewing is readily available and of excellent quality, rigorous quality. And the Math Assistance area has published DIY, that means do-it-yourself reviews. And so you can just go to the Learning Commons website and click on do-it-yourself reviews, and then they give you a choice of some things, and you click on algebra, and this will take you to a section that is called logarithm solving, logarithmic and exponential equations, but this includes logarithm basics, solving logarithm equations, solving exponential equations, and graphing exponential and logarithm functions. So this is an excellent review that's available as you need it. They have screened some YouTube videos, they have example problems, and they have solved problems with complete solutions. Again, very well done if you need it. Okay, so let's do some calculus, and we're going to start talking about e to the x. Now, e to the x has the base e, that's that 2.71 number, and the variables up here, but often e to the x is written as exp, standing for exponential of x, for clarity, to show that it is a function and to help people understand that better. So let's begin with the definition of the derivative then. So the derivative with respect to x of the exponential of x, e to the x, is going to be the limit as h goes to 0 of exp of x plus h minus exp of x all over h. And now going from here to here, we use a property of exponents. So e to the x times e to the h is e to the x plus h. That's a property of exponents. We're using it backwards though. So we're going from here to this. And now what we're going to do is we're going to do some algebra here because we have two terms in the numerator. We're going to factor out the e to the x from this term and from this term. So we factor it out, and now we haven't taken the limit yet, so this is still the limit as h goes to 0, but now as e to the x times the quantity exph minus 1 all over h. Now this limit is on h and it's going to 0, but e to the x has no h in it, so as far as this limit is concerned, it's a constant, so I can pull it out of the limit sign. So this is going to be e to the x times whatever this limit is. So this is the limit as h goes to 0 of e to the h minus 1 all over h. And what we're going to do is evaluate this limit, and we're really going to see that this limit in the parentheses here really is 1. So that means the derivative of e to the x is e to the x. That's kind of an amazing thing. Here you have a function whose derivative is the function itself. But let's be complete, and we're going to talk about this limit a little bit to convince ourselves that it really is 1. Now, we talked about three ways to do limits. We could do them analytically, we could do them graphically, and we could do them numerically. Now later we're going to learn more math and we'll be able to prove this rigorously analytically. But right now let's just look at what the graph of this looks like. So here is what I'm doing is I'm graphing along here. This is the function. This is like e to the x minus 1 over x. And I graph it, and you see now h can't be 0 and x can't be 0 over here, so there's a hole in the function, but you can readily see that the limit as you come from the left is 1 and the limit as you come from the right is 1. And so this example makes you feel, oh, that's what's going to happen. I can also take numbers that are approaching 0 from above. So here I got 1, here I got a tenth, here I have 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, this is 10 to the minus 6. And you see that this expression, e to the h minus 1 over h, is getting closer and closer to 1. Similarly, if I pick numbers closer and closer to 0 from the left, I get closer and closer to 1. So 2 out of 3, and later on we'll do this other part, but it's reasonable to conclude that this is 1, and so we've confirmed that this is 1, and so the derivative with respect to x of e to the x is e to the x. And so here's your fundamental takeaways then. The derivative with respect to x of e to the x, or e to the x prime, is e to the x. But we've studied the chain rule. And so if instead of x we had a function of x up here, we know that the derivative with respect to x of e to the u, where u is a complex function of x, is equal to e to the u times du dx. You want to remember both of these. These are fundamental takeaways. But let's apply that now to a problem, and this is one of the fundamental problems that we study in calculus, is find the tangent line to y equals f of x equal 4 times the square root of 2x minus 6, and then this is e, the number e, raised to the 2 minus x. And we want to find the tangent line, and in fact the equation of the tangent line at x equal 2. You know what to do, and so I suggest you pause the video and give this a go. Let's see how you did. Okay, well, we need to know the derivative of this function, and as we often do, we're going to rewrite this function. So that is 4, this is 2x whole to the 1/2 minus 6e to the 2 minus x. Now notice that that's a u there because it's not just x, it's 2 minus x. So we're going to take the derivative and we do each term. Now the 4 just sits there, but here I use the power rule and the chain rule. So this is going to be, the 4 is just sitting there, but now I take the derivative of 2x whole to the 1/2. That is 1/2 2x whole to the minus 1/2. And then by the chain rule, it's times 2. So there's the derivative of that, minus 6. And now I have to take the derivative of this. But the derivative of e to the u is going to be e to the u times the derivative of u with respect to x. Well, u here is 2 minus x, so du dx is going to be minus 1. Now, if you simplify this using the algebra, what you will get is this expression, and note that a minus times a minus becomes a plus, and then I could write it in a different form. So this is 4 over the square root of 2x plus 6 e to the 2 minus x. Now, we do have to evaluate both the derivative and the function when x is equal to 2. So f of 2 is going to be equal to 2. Notice that e to the 0 is 1. And f prime, which we found up here at 2, is going to be, again, e to the 0 is 1, is going to be 8. So we know the slope is 8, and we know the y value is 2. So I can say y minus the y coordinate is equal to the slope, f prime at 2 times x minus the x coordinate. I could simplify this, and I can find in slope-intercept form that y is equal to 8x minus 14. Now, moreover, since we were using e as a base, you might say, oh, but there could be other bases that I could have. And so it's important that you recall from your pre-calculus that 2 to the x can be written in this way. You see, since e and the natural logarithm are inverse functions of each other, e to the ln2 is actually 2. So I'm replacing 2 with this, but then I use my properties of exponents. Here you multiply the exponents. So this is e to the ln2. That's a constant. That's a number times x. So you see we've got a u here. So if I take the derivative with respect to x of 2 to the x, that's the same thing as taking the derivative of e to the u, which is going to be e to the u times du dx, but that's a constant, so I get the derivative of 2 to the x is the natural logarithm of 2 times e to the ln2 x, but e to the ln2 in the middle here is really just 2, so this formula can be simplified. So the derivative with respect to x of 2 to the x is the natural logarithm of 2 times 2 to the x. And certainly we always have to be mindful of the chain rule, and so the chain rule would read as follows. The derivative with respect to x of 2 to the u is ln2 2 to the u, and then times du dx by the chain rule. And this doesn't work just for 2, it works for any a greater than 1. All you need to do is replace the 2 with an a, and you're good to go. Now we're going to turn our attention to logarithms. Recall also from your pre-calculus studies that when I say y equal the logarithm base e of x, that's the same thing as saying that e to the y equals x. This is called the exponential form. This is called the logarithmic form. And this is going to be key to what we're going to be doing, because we're going to take so here is y equaling logarithm base e of x, and we want to find dy dx. But it turns out it's easier for us to consider e to the y equal x, and what we're going to do is finding the derivative of y with respect to x using implicit differentiation, which is why we studied it the other day, one of the reasons we studied it. So when I take the derivative of x with respect to x, I just get 1. But when I take the derivative of e to the y with respect to x, I make note of the fact that y is a function of x. So the derivative of e to the y with respect to x in this case is going to be e to the y times dy dx. And then, as we always do, I'm going to solve this for dy. So I'm going to divide both sides by e to the y. And I can divide both sides by e to the y because it's never 0. And so we find that dy dx is equal to 1 over e to the y. But e to the y was x. So this is 1 over x. So you see the derivative of the natural logarithm, the logarithm base e of x is 1 over x. It does grow very slowly. In a similar fashion, what we know then is that the derivative with respect to x of the ln of u, if u is a function of x, is 1 over u times du dx. That is the chain rule. You see how we're building on everything all the time. And moreover, in your pre-calculus, you did study a change of base formula. And there you learned that the logarithm base a, this is not necessarily e, the logarithm base a of u is 1 over the natural logarithm. This is a symbol for the logarithm base e. So this is 1 over the natural logarithm of a times the natural logarithm of u. So this is in the numerator, that's in the denominator. And this is a constant because a is a constant. So when you take the derivative of this, so this change of base formula tells you that when you take the derivative of this, you can pull this constant, 1 over natural logarithm of a, through the derivative sign, and you're taking the derivative of the natural logarithm of u, which is going to be 1 over u times du dx. So you have another formula for any a logarithm to any base a. Now let's use this to solve a problem that again is one of the classical problems that we solve in a Calculus 1 class, and that's determining where in an interval, in this case it's going from -1 to 20, this function y equals f of x equal the natural logarithm of x to the fourth plus 20x cubed plus 100. Where is this increasing and where is it decreasing? You know what to do. Let's see how you did. Okay, so we're going to take the derivative of the logarithm of, this is the logarithm of u. So this is going to be 1 over u, and u is x to the fourth plus 20x cubed plus 100 times du dx. So this is 1 over u, and times du dx is the derivative of this. That's going to be 4x cubed plus 60x squared. And since I am going to be trying to figure out a rate of change here, what I'm going to do is I am going to factor this. I notice there's a common factor in the numerator of 4x squared. And so this is 4x squared times the whole of x plus 15. So we did take the derivative, and now we're going to study what's happening with this. The derivative gives us the rate of change. So when the derivative is positive, it's going to be increasing. When it's negative, it's going to be decreasing. And one thing you should note is that the denominator, as we're from -1 to 20, the denominator here, when you think about this, you're adding 100, which is a big number relative to those. It's greater than 0 throughout the entire interval. So this bottom is always positive. So all we have to do is say when is the numerator negative, and that will help us. Okay, so we need to know where the function is not changing, and then we know when it is negative and when it's positive. So what we're going to do is set the derivative equal to 0 where it's not changing and solve. Now the denominator is never 0 in that interval. In fact, it's always positive. And the numerator, we're saying when is this equal to 0? Well, it's equal to 0 when the numerator is equal to 0, 4x squared times the whole of x plus 15 equals 0. And so it is at 0 when this one is equal to 0, or at -15. Now, we don't really need to care about -15 because -15 isn't in this interval. So we're really going to be looking at x equals 0. So that's the only point we need to see what happens. And when we look, we'll find that and here's a number line, and we can see that f prime at -1, we're plugging numbers into a calculator here, is positive, and so that means that f prime is greater than 0 here, and you could pick another point here of 1, and you see it's always positive. So anywhere in this interval except x equals 0, because where it is 0, this is a positive, so it's always greater than or equal to 0. So it's increasing except at this point. So to summarize then what happened in this video, we learned that the derivative with respect to x of e to the x is e to the x. We learned that the derivative with respect to x of a to the x is a to the x times ln of a. We learned that the derivative with respect to x of the natural logarithm is 1 over x, and we learned that the derivative with respect to x of the logarithm base a of x is 1 over x ln of a. And please remember that there are chain rule versions of this as well. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself, because self-care is important, and take care of each other. We're all in this together. God bless you all.